Okay. Yeah, so thank you for coming. My name is Tom. Here is Shachar. We're both from Starkware. And I mean, this is a bit fancy, but the intention of this workshop is to be not formal one. So, I mean, we will present StarkNet. We will go through a demo of how to write and deploy StarkNet contract, and then you would also try and succeed to write a StarkNet contract. But feel free to ask anything that you want on StarkNet, on Ciro, which is the underlying language that we won't get much into. But basically between Shachar and myself and Louis, everything about StarkNet and Ciro and Starkware in general is here, so just feel free, okay? Okay, great. So, yeah, as I've said, our purpose today is to write StarkNet contracts and to deploy them to StarkNet Alpha, which is a work-in-progress version of StarkNet that we published on Ropsten, and we're constantly updating it with the latest state of our development. So I'll start with saying, on high level, what is StarkNet, what we're aiming for, then a little bit a deep dive into StarkNet, and specifically what are the changes from this perspective of developer with regards to Ethereum. Then we'll do an intro to Ciro, which will be a very brief overview of Ciro, which is the language in which the contracts are written. And then Shachar will show a demo of writing a contract, and then you will be able. I think it will take between 1.5 hours to maybe more, and feel free to stay afterwards and keep talking. But let's start. Any questions before I start? Okay, great. What I wanted to say, maybe you should write it before I continue. We tried to put all the resources which are relevant to this workshop in this resources page. And we tried it to be a simple URL. So write it down and let me know when you're finished. Someone still writing it? Okay, perfect. So let's start. Okay, so what is StarkNet, or what is the vision, or what are we aiming for? So basically, it's a layer 2 network on top of Ethereum, which will be permissionless ZK rollup, and it will offer both scalability, right? This is why we're doing it. Yes? Yeah, sorry. So both scalability and the security of Ethereum, right? So just trying to break it up. So basically, it's a ZK rollup. I crossed it because it's not really ZK, right? ZK stands for zero knowledge, and it is not used here in anywhere, zero knowledge. What we actually use are validity proofs, and the fact that verifying a validity proof is exponentially less computational heavy than the computation itself. So we actually prefer to call it validity rollup, but the actual term is ZK rollup, but now you know it. It will be permissionless, both of course for the developers and users, but also for the sequencer level. So sequencer levels are the equivalent to miner in Ethereum, and this layer will be permissionless. The contract will offer basically implementing any computation that you want, and you will be able to see it today. And we will also have composability, meaning contracts will be able to interact with each other and also with layer 1 contracts. Okay, great. So this is the vision, what we have today. So today we at the StarkNet Alpha 1. Last month, on the mid of June, we released StarkNet Alpha 0. On Monday, we upgraded it. So basically, what's StarkNet Alpha? As I've said, it's a work in progress. So currently, it's not a network. It's a hosted service that we are running. But it allows to see what is the state functionality of StarkNet today. So it has smart contracts, meaning you can write and deploy smart contracts to it. Users and anyone can send transactions to those contracts. There's also layer 1, layer 2 interaction, meaning layer 1 contracts can send messages to layer 2 contracts, and layer 2 contracts can send messages to layer 1. And the next update will include the composability, the layer 2 to layer 2 interaction, right? And I think it's the first system, and maybe I'm wrong, but as far as I know, it's the first system that actually lets you do all those stuff, and the state updates to this network are proven off-chain and verified on-chain, meaning each transaction, deploy transactions, interaction transactions are batched together, approved, and when you do a state update on L1, which I will get into it in a second, it is backed by a validity proof. Is this clear? Okay. And as I've said, we keep updating the alpha. And the next thing that we will update will be the inter-contract interaction, which will open up what experimentation can be done with this system to a much wider variety of use cases. And I'm not going into a full overview of StarkNet, but I mean, a view, which is, maybe I think you saw him in the entrance, gave a talk today at EthCC, which I don't yet have the link, but it will be available, and you can have like a wider overview on what is StarkNet. Okay, so now let's, yeah. What's your name? Christoph, hi.
Just to have some view, when you're saying that next will be composability and there will be next steps, like, what does the roadmap look like?
From timeline perspective. Yeah, so Christoph asked, what exactly is the timeline? I mean, when does layer 2 interaction is supposed to come, and when we actually, I guess, when we aim to launch on mainnet? I just repeated. Thanks. Okay, so we're already working on it. I think it will be in the order of between months to 2 months, this specific, and we're aiming to launch with the beta network on testnet somewhere around Q4, right? And hopefully to take it a step further to mainnet by the end of the year, or maybe at the beginning of next year. There's like what I'm describing here is we call it the StarkNet core, because it's the actual functionality of the state, right? So there's a whole ecosystem around it, which there's also either internal work or external work that works on it. But here I'm just describing, I mean, what a developer can do with contracts. Okay, thank you. Any more questions? Okay, so I mean, we tried to list the properties of StarkNet that are relevant from the developer perspective. Maybe we missed something, and if you have questions along the way through the demo or when you're writing, then feel free to ask. But basically, when you look at the consensus mechanism of a layer 2, specifically ZK rollup or rollup in any rollup, so what defines the consensus is the state which is committed on the L1 contract of the system, right? So when I do a state update on L1 and it is accepted because a valid proof was also verified on L1 and another list of properties was also verified, then we say that the state was updated, the system was updated, has updated to a new state. And this is relevant because it means that we have like 2 types of finality. So one, we have the off-chain confirmation, which means that at this point, it means that the sequencer, our service said, okay, this will be included in a block, and this is the state after this block was executed, but it still hasn't made the state update on L1. And the second step of finality is the L1 finality, after which this state update has actually occurred. Specifically now on Ropsten, since the upgrade of the network to EAP 1559, So there are very, very deep reorgs because of one rogue miner. And we are in the transition to moving out of Ropsten to Goerli, but the actual confirmations on L1 that we are waiting is very, very large. So it takes, it is not the best experience right now. Hopefully next week we'll move to Goerli and we'll be back to, I don't know, on the order of minutes. But now it's 120 blocks confirmation, so there's a big latency. Okay, this is the finality aspect. The other aspect is a contract. So as I've said, they're written in Cairo, and Shachar will, in a minute, give us a brief overview of what is Cairo. But the actual contract structure is the same as EVM contracts, meaning basically you have storage variables, which can be either just a variable or mappings of mappings. And you have functions, internal and external, and view functions, which operate on those storage variables. They can also send messages to L1. And in the next update, they will be able to also call other contracts. And one thing which is different from Ethereum is account abstraction. So on Ethereum, an address in the state has few properties. One of them is balance and nonce. And I guess you know that, but if it doesn't has a contract deployed into this address, then it operates as an externally owned account, meaning it can send transactions. So basically, every transaction in Ethereum origin from one EOA address, right? So in StarkNet, this is not the case. All addresses are contracts, and account functionality is implemented as a contract. So we will have a account contracts. And what does this mean is that transactions has no signature, and the signature is actually verified on the application level. So when you will want to send a transaction in StarkNet, you will see that you don't need to sign on it in advance. And if you want it to be somehow verified, it needs to be part of the inputs to the transaction. Was that clear? Okay. I see faces, but I will try to go at it from a different angle. So when you send a transaction to Ethereum, it must be accompanied with a signature. And the signature is verified on the protocol level. What the protocol actually verifies that who signed on this signature, and then it verifies that this address has enough funds to pay for this transaction, and then it calls either a ETH transfer or whatever function this transaction wants to call it in a specific contract. And in StarkNet, there's no verification before actually calling the contract. You immediately call the contract, and if the transaction can be executed, it will be executed. And if we want to mimic some account functionality in StarkNet, we actually do it through an account abstraction. I don't think it will have any meaning right now, but you will see that when you want to send a transaction, it doesn't ask you to sign on it or stuff like that. Okay, we'll see how we handle signatures in the demo. Okay, so this is, I think, the relevant properties currently from StarkNet. Shachar, you want to explain a little bit about Cairo?
Hi. So this will be a very brief introduction to the introduction of Cairo, because there's a lot to talk about in Cairo. If you are interested in learning more about Cairo, you can see in our resources a URL that you saw in the beginning. There's a link to the StarkNet documentation. From there you can reach the Cairo documentation and learn more. Okay, so a few things about Cairo. Cairo, okay, it's very efficient in the sense that we want to compile a sort of a ZK proof from program, and that is why there are some decisions that are not standard in programming languages. One of them is that memory is immutable. So if you assign some value to a variable, you can't reassign anything. Also, it means that it's hard to do loops because you don't have an iterator that can change values. Instead, you have recursion. So it's sort of like a functional language. Also, in the resources section, you can see a cheat sheet, which I want to go over now. So let me just...
Maybe just say a sentence about what is Ciro, because we didn't say.
Oh, yeah. Okay, Ciro is a programming language designed to create ZK Stark proofs. Essentially, you can write a program in Ciro and then run it locally and then give it to a prover that will generate a succinct proof that you can verify very efficiently. This program ran with these inputs and gave this output. So, for example, if you want to implement an exchange, for example, the program would be something like it reads transactions from the input, it executes them, applies on the state, it has some mapping of balances, it applies the balances, it verifies signatures on the transaction from users, and then it outputs what is the hash of the final state. And from this run of, like, let's say we have 1,000 transactions, then you can generate a small proof. You can put it then in L1 in Ethereum, where we already deployed a Ciro verifier contract for you. Anyone can use it, and if the fact is written on chain, you can be sure that if you start with a state with this hash and apply some signed transactions, then you'll get this hash at the end. So Ciro is meant to make efficient proofs of computation. Anything else?
Yeah, maybe I would just add, I mean, there's a very nice presentation of Shachar on how we created Ciro, but for the sake of StarkNet, StarkNet is basically abstract all of this, most of those things from the developer, and allow him to, or her, to write contracts the same way that you are used to. So, I mean, Starkware products, for example, StarkX, is written in Ciro, and it's a specific ZK rollup application, but what StarkNet does, it brings a blockchain framework that allows to prove state updates of this blockchain because of Ciro. I hope it was.
Any questions about Ciro? No. Okay, so I think we can start with the. Let's say we need the to onboard them, right? To a quick start on setting up your environment. Yeah. No, I think we'll get them starting, and then we'll do the cheat sheet. Okay, so let's start with setting up your environment. You need to download things, which
Yes, you have this link on the resources page, setting up your environment. And basically, yeah, so this is it.
yeah. So take a few minutes to go to that link from the resources section and set up your environment. If you have any questions, you can ask. Basically, just good practice is creating a virtual environment for Python. Then you should download the package and pip install it. There are some prerequisites, and then you're all done. So
after you did it, maybe you can go back to the presentation. Let's
Okay.
go back to the presentation.
okay. yeah, and then do these things. If you manage to run this line, then you're good. Yeah.
What if I have an Apple Mac with ARM processor, like Silicon, Apple Silicon, then Python 3.7 won't work.
You have M1?
Yeah.
It's a good question. We haven't updated
Uh,
here to M1, so I don't know. But have you tried?
Yeah, I'm trying, but not sure.
In Python 3.7 doesn't work?
Oh, it doesn't work. Yeah, that's for sure. Those two, but
And some other Python work?
well, first of all, okay, I got a question. What if basically this doesn't work? First of all, you can go to the playground at the Carol Lang site. It's just a web version. You can deploy your contracts from there, so you can play around with it there. It's always an easy solution. Otherwise, virtual machine.
what was that called?
Ciro-lang.org. There's a playground there. Though I do recommend you try to set up your local environment if possible.
Will the playground be sufficient for following this entire workshop?
There will, okay, there was a question if the playground is... it will be okay for most things, but not 100% of the things. So if you can set up your local environment, it's better.
Is it possible at all to set it up on M1?
Yeah, we don't, I mean, we haven't tested it on one. But I think the playground will be alright.
Seems to be way.
You know, if you have Apple and you have problems installing it, then it's really your fault because you're using Apple. So stop. Does anyone need more time to set up his environment? Don't be ashamed. Say this, okay. Remember to do these steps as well. Just this and make sure StarkNet works. You can also see it on your resources link from the beginning. Alright, so. Okay, let's continue. Okay, so this is the cheat sheet that you also have the link to in the resources page. It's just like a very brief overview of things you can do in Cairo, and you can, and it's the syntax, of course. You can define structs, user-defined structs, like this with a struct. Define members. Felt is the basic type in Cairo. It's a field element, and basically mathematical operations on it are in the field. If you add, it's in the field. If you multiply, divide, it's in the field. This can also give rise to weird results. If you multiply two numbers, you can suddenly get a small number. You can get 1 because it's in the field. We'll see later how to do safe arithmetic operations. The asterisk is pointer. We can have pointers. Functions. This is the syntax for function. Inside this is the arguments. For example, these are 3 arguments. These are the return types. Have multiple return types. These are your return. You can return either without argument names or with argument names, also when calling functions. When you call a function, you can either call it discarding the return values or bind them like this. Okay. Basic function calling. Import. You can use the this import syntax to import things mostly from a standard library, which has a lot of things we'll see in the next few bullets, but also from your code if you want to split it over files, obviously. There is the main function in Cairo. When programming in StarkNet, you won't ever use the main function. It's written for you. It's already generated, but in regular Cairo, you have the main function. Other than that, this is how you can allocate an instance of T. You use the alloc function. Instance will be pointed to a T type, and then you can start filling its members using the assert keyword. Assert basically makes sure that the left side of the equation equals the right side of the equation. This is where Cairo is like different from a regular language. Because it's a language for verifying things, it is non-deterministic, and writing values is the same as verifying that they equal something. And the Cairo runner automatically knows to deduce that this memory cell needs to be equals this, and I don't know this one, so I'll make it equal. If you want to dive more than the documentations, but practically this is how you write values to the members. Variables. At the top of the function, you should write alloc locals if you want locals. Yeah. It will change in the future. I'm sorry. This is how you define a local of type T. You can also assign where you define the local. When you bind the return value from function, you can add the local to make it local. We should use if the compiler yells at you. You can also rebind. For example, I had a local B before. Here I rebind it. So B right now is actually this second variable, not the first one. And note that I can't write again because it's immutable. The memory is immutable. So rebind is not the same as writing a new value to B. For example, if you had a pointer to the old B, then the old B would still point to 4, even after this rebind. Okay. Implicit arguments, you will mostly see them in the code. You won't need to use them yourself, although you could. But if you use this syntax, this means it's an implicit argument to the function. So you don't have to explicitly pass it, but it also it's also an implicit return type. So this function, basically under the hood, gets A. Inside I can do things to A, we bind it, and then it returns A to the caller. It's good if you have like pointers that are advancing and want to treat it like something mutable. Then we pass it and get the new value. For example, this is how I called foo, and I don't need to explicitly pass A, but it's passed and returned. And notice that I can also use this syntax, pass A, and it changes the value of A. Okay, conditionals. This is very useful. Just you do if something equals something, or something different than something, you can have the else. This syntax looks a bit like Python. Try to avoid defining locals inside. You can see the cheat sheet for extra details. Oh, okay. Now built-ins. Built-ins is also very important. Because we want Ciro to be very efficient, we don't implement everything in Ciro. For example, the hashes and the signatures. If we would have implemented them in Ciro, they would be very expensive. So instead, there are some built-in with a very efficient implementation in polynomial equations. And the way you use them is basically pass this implicit argument and use the library function. So for example, this is the built-in that does the hash, and you can use the library function hash2 to hash two values. You also have the same thing with the verify ECDSA signature. This is the two basic built-ins you will need to use. Okay, for the signatures, in order to, this is not Ciro code, this is Python code. In order to sign using our curve, this is like a sample Python code you can run in the environment you installed. This is basically signs things. We will use it. Some arithmetics, like I said, these are all field operations, adding, multiplying, dividing. We have library function for asserting not zero, asserting non-negative, which actually means that the number is between 0 and this big number. So if we want to do safe math, then we need to use numbers that are always in the bounded range, like 0 to 128. Basically assert that all your inputs are there. After you add things, assert it's there. After you multiply, maybe you need to assert it. Maybe even use the assert NNLE to make it a lower range. For example, if you want to only support amounts with 64 bits, then assert everything is between 0 and 64 bits. And you also have this nice function that does integer division as opposed to field division, which are different things. And there are also the versions that instead of asserting, they just return if it's true or not, like 1 or 0. Dictionary is also very useful and important. Like I said, Ciro is a mutable language, so it's hard to use dictionaries which are mutable by nature. But we have some magic that does it. You can look at it like this. We have the function that creates a new dictionary. We have the dict read and dict write. And at the end, you must call dict finalize, otherwise it's not safe, basically. Okay, this was a bit about Ciro. StarkNet has like a version of Ciro which you don't need to write main, and you have extra things to which are syntactic sugars for your contracts. For example, we have the storage var, which is how you have storage in your contracts. Yeah, it's not immutable. For example, these three lines define a single variable in the storage of type field element. You can read and write it using this dot read and dot write. You can also have a lot more complex storage variables, which is like a mapping from two field elements, and the result is a pair of field elements, and you read and write like this. So it's like a map of a map with a value that is complex. Okay. Other than storage vars, you have the external decorator, which means this is a function that can be called from outside, from other contracts, directly from user, from transactions. This is the external. So instead of having a main, you have external functions. And the external functions can have either just field element arguments or arrays, which must look like this. One defines the length, and the other is the array, the pointer to the data. Okay, this was. Yeah, we also have a view function, which is like external, but you can also use it with the call a CLI, which basically doesn't make a transaction, just it does it locally and doesn't change the state. Okay, so this was a very, very long, brief introduction to Ciro. Yeah.
Are the built-ins open source?
Okay.
Will it be open source?
Okay. Okay. Essentially, they are. Built-ins have a few parts. Like the part in the. Okay. The question was if the built-ins are open source. So the built-ins have a part in the Ciro runner, which is how we run the VM like unrelated to the proof itself, just running it in virtual machine in our computer. That is open source. You can see it today. Other than that, there are the equations, which you can also see in our contract. There is a Solidity contract that is deployed and everyone can see. The equations, the polynomial equations that verify the built-ins are there. The thing that currently isn't open source is just the prover side of them, but that is maybe will be released under the Polaris license in the future. But most of the interesting things about built-ins are open source.
Specifically the things that are needed for trust.
Yeah, specifically the things that are needed for trust are open source. Okay. Any other questions? Okay, you have this cheat sheet. You can use it when you will write things on your own. Okay. So I want to start with showing you how a contract looks like. Oh, also, if you're using VS Code in the setting up your environment part in our site, you can see it in the resources part. There is also a link to a VS Code extension that makes your life easier when writing Ciro. Okay. Let me just do a duplication. So we'll see the same thing. Okay. So this is a sample contract, just a really simple one, StarkNet. Let's see how it looks like. Let's break it down. StarkNet contracts always start with the lang StarkNet, which specifies it's the variant of language that is used in StarkNet. We then give the built-ins we will use in this contract. Then all the imports, we have the hash built-in and the storage, which is relevant to storage. The first bit we can see here is what we saw in one of the last cheat sheet elements. It's a storage var. It's basically a balance. We have one variable of balance in this entire contract. It's not a mapping, just one field element. We have one external function that increases this balance. It gets one argument, amount. The other are implicit and they are built in, so it's not very important. It gets the amount. What it does is read the balance and adds the amount. Not very complicated. The other function is a view function, which you can use in the call, which you'll see soon. It gets no arguments and returns one value, which is what you get from reading the balance. So pretty simple. Basically one variable with a setter and a getter. Any questions about how what happens here? No. Okay. So let's see what we can do here. First of all, okay. You should all have the StarkNet compile CLI command. I tell it to compile this file and output both the compiled bytecode and the ABI, which I can use to make call and invokes later. Okay, so it's compiled. I just want to say, if you want to do this thing with me, you can download this contract in the docs. Like the resources URL we gave at the beginning, there's a link to the StarkNet docs. There's yeah, and in there is the first contract, so you can go there and copy this and do these commands on your own. Okay, so now that I compiled it, I can deploy it using StarkNet deploy. It's pretty easy. StarkNet deploy and the contract. Okay, so I initiated the deploy. There's a transaction ID and the contract address. What I can do now is let's see, StarkNet. Let's see the commands I have in StarkNet. Oh, I have the get transaction, which you can see. I can give the transaction ID and see what's up with my transaction. Okay, it's received. What I want to do is wait a bit until the status is changed to pending. Pending in the second form of finalization we have, like Tom discussed before. After a transaction is received, we need to wait for it to be batched in some batch, which is the consensus mechanism, but it's still not in L1. And after a longer period, when a proof is generated, then it will also be in L1, and that is the final confirmation. Right now, to work with it, it's enough to have it pending. We also have a web UI for it, the Voyager. Voyager Online. We can check the transaction over there, which is V22. You can see it's still not inside a block. By the way, you can look at all this transaction, what they did, look at the contracts, and read and write from the contracts. Okay, so transaction is inside, so you can see here. This is a transaction 37 seconds ago, sent to this contract. We can see the functions we have get balance. If we just query the get balance, we get 0 because we haven't did anything inside. And also notice that it's a getter for a single variable. It's not anything amazing. we can increase the balance, but I want to do this from the CLI. So let's do it in the CLI. First of all, just notice that now the status is pending. This is second confirmation. Okay, so let's do a call just to make sure our call will be reasonable. We call the function increase balance. Let's see what else I'm missing. Address and API. This is the address. Hope. And the API is one of the artifacts of the compilation I had. And I need to add an argument at the inputs. So I'm adding balance, how much I want to add. Let's say 1, 2, 3, 4. Okay, so the call passed successfully. So I'll just do the invoke. Invoke actually makes a transaction and sends it to StarkNet. Okay, now I have a transaction ID. And I can wait for it to be accepted. And once it will be accepted, I will be able to do the call on get balance, and I will see my balance. We'll do it in a minute. So this is the basic interaction with StarkNet. Are there any questions on this interaction? No. Okay. So right now I want to add some functionality. Like having balance for one user is kind of silly. So let's add a user. I want the balance to be a mapping right now. So I'm adding an argument here. A user. And now it's a mapping. Now it tells it me that, hey, don't have enough arguments here. So let's read user equals user and add it as an argument. Yeah, user is undefined, so add it as an argument to the function. And when we write, I can't mix, right. Let's do like this. Okay, so increase balance is okay. And now get balance, I need to do user equals user. Okay. What? Yeah, also I need to add the user as an argument. Thanks. Okay. This wasn't very hard, I think. And by the way, let's look at the previous thing we added to the balance. Right now, the transaction we invoked before, adding 1, 2, 3 to the 1, 2, 3, 4 to the account balance, we can see it's here. This is the balance. Okay, go back here. Okay, this is nice, but I also want to add some authentication mechanism. Don't want to let everyone increase the balance of everyone. I want to add some signature for the user. So what I'll do is add as an argument the signature here. Let's say the signatures in a Ciro are 2 field elements, RNS. And I'll need to use a signature. I have my cheat sheet here. Yeah. These are the required imports. And just let's see this function. Where's the cheat sheet? Nope. Do not look at that. Okay. cheat sheet. Where's my cheat sheet? Here. Okay, this is a cheat sheet. So, okay. This is how I use the verify CDSA signature. And here I'll also verify. Doesn't really matter where, but I'll verify. And let's say the message I want to just the amount. And it's basic enough. User should just sign the amount. The public key should be user. And yeah, this is already here. Oh, okay. So right now it yells at me that I don't have the ECDSA built-in passed. And indeed, we can see we only pass it the hash built-in. So just add the ECDSA built-in. Doing it in one hand is not helping. Okay, and now it says that it doesn't know, like it's an entry function, it's an external function, it doesn't know what to give ECDSA because I didn't add it in the built-ins. So I'm adding ECDSA in the built-ins. Okay, and now everything should work. So again, let's compile. Compiled, it's good. And I'll deploy it. And now we just need to make a valid signature, right? Call it with the right arguments. So for this, we have as I showed you as you can see in the cheat sheet, how to create valid signatures. So this is an example. And this is like creating a private key. Let's say this is my private key, very safe. And I'm making a public key, and I'm also signing the message 4321 with this private key. So this thing will be our user, the public key, and this will be R, and this will be S, the signature. We'll give it. So let's do the invoke. StarkNet invoke function. I want to do increase balance again. Now what are the arguments? Okay, probably also missing address and things. No. This was the address. Yeah, this is this is the address. Are you saying I forgot to do oh, yeah, this is the contract. Thank you. This is the address and the ABI. Contract ABI. This is a function. And the inputs are, let's see, user. This is our user, the public key. Amount, we signed 4321, so that's what we need to give it. RNS, signature. And this. And before we do an invoke, let's do a call. Okay, so the call passed. If I would have passed it a wrong signature, for example like this, then it would yell at me because it's the wrong said transaction failed, the wrong signature. So signature mechanism works, which is good. and instead of a call, do an invoke to actually do a transaction. Okay. So basically, what we did here is added this complex mapping instead of just a single variable, and we also verified signatures. As you remember from Tom's talk, we don't have users don't sign transactions when they send them. So basically, anyone can send anything unless, at least currently, you enforce it in your contract. Like in the future, we'll have probably account contract, so you can rely on the sender of the transactions. But currently, we need to verify the signatures inside the contract itself. Okay, are there any questions on what we did here? Oh, you guys are good. Okay. So next thing I want to show is a L1 communication. Did I forget anything for that? Okay. So, okay. L1 communication works both ways. You can send messages to L1 and get messages from L1. So let's see my cheat sheet here, how it works. Yeah, I have it. Okay. Oh, I have it here. Okay, this is an example of this is basically what we did before. And now there are additional functions, which let's go through what they do. Okay, it's a withdraw and deposit. A withdraw is basically something I invoke at L2. It reduces some balance from L2 and then sends a message to L1. Let's see how it looks. First of all, we verify that the amount is indeed in the right range. It's non-negative, so no, because we withdraw, we want to reduce the amount, not add it. So make sure it's not negative. Note that to use this thing, we must pass the range check pointer. This is what allows us to do all these arithmetic operations. Okay, so now that amount is good, we read the current balance and deduce and verify that the new balance is not negative, that user has enough balance. And then we write the new balance, and okay, at this point we deduce the amount, and we need to send a message to L1. So we create a field element array, basically just using the alloc. And we write 3 words. The first is some identifier, some selector that mentions, hey, this message is of type withdraw. And the next is which user did it and with what amount. Back at L1, we should have a corresponding Solidity contract that can parse this thing. And we'll see it shortly, this contract, how it looks like. Okay, so now that we have this payload, we just use the send message to L1 library function, which we import, to L1 address, which we defined here, L1 contract address, just number, and the size of the payload, which is 3, and the payload itself. Just sending a message to L1. Now, how? Yeah, exactly. And like in the same way that for using assert NN we need to pass the range check pointer, and to use send message to L1 we need to pass the syscall pointer, which lets you do some StarkNet system calls. Okay, so how does this L1 content look like? I had it here somewhere. Here. Let's just have a brief look at it. Okay, first of all, there is a. Okay, this is so you know how to write the counterpart Ethereum contract that talks with your contract. There is an interface you probably get from somewhere else, the StarkNet core, which has send message to L2 and consume message from L2. So basically, when you send a message to L1 in your contract, it still doesn't automatically apply to L1. Someone needs to issue an Ethereum transaction to do it. Like in the future, we have something automatic that does it, but right now, you need to issue it yourself. Yeah.
When a contract sends a message to an L2 contract sends a message to an L1 contract, then when we do the state update on L1, then part of the output of the state update are those sent messages to L1. So, and then it gets stored on the StarkNet Core L1 contract. And as Shachar shown here, the interface, L1 contracts can consume these messages. So for example,
Yeah. Okay. For example, if you see the withdraw function, and then it creates the same payload that we saw before, and then it basically says, hey, make sure you got this specific message and consume it, to like mark that it is consumed. And once we get here, we indeed got this message, and we add this balance to L1, basically. So using consume message.
Is it clear that the L1 and 2 messages protocol? What consume message does? Does it only read or
No,
that's the counter?
yeah,
It means you use
it marks this flag of consume, basically.
yeah, we use counter because there can be multiple same message. We say I'm a user, I want to, I don't know why, withdraw 3 times, 1 hit. So the message will be the same message, right? So I don't want it to be true or false. Okay? If I consume,
Okay. Okay. Everything is fine.
it's fine, it's fine. Okay, thank you.
Okay, yeah, I just want to repeat the question. The question was, what does consume message actually do? Does it only read? The answer is no. It also marks that the message is consumed. The implementation is there is a mapping at L1 from the message hash to an integer. It starts with 0. Every time a message is sent to L1, we increase 1 to this number. And when we call consume message on L1, we deduce 1 and say, it passed.
So the messages has to be like, is it like all the messages have to be consumed in the correct order? So for example,
No. The question was if it must be consumed in the same order. Then no, the messages are unordered. There is no order on the messages. You consume it in arbitrary order. Okay, so this was sending message to L1, and this is the opposite direction. If we get a message from L1, okay, the Ciro contract has this decorator which says L1 handler. Basically, if you see the solidity part, then the deposit creates a payload that will be passed, and when it calls, we use send message to L2. We give the L2 contract address. This selector of the function, which will be generated from this function name, basically, it's a sort of a hash, which there is a tool to deduce this selector, and the payload. And then, after you do it in L1, then automatically a transaction will be added to L2 that calls this deposit with the correct from address, which is an Ethereum address, and the payload as arguments, the user and the amount. Okay, so what we need to do here is, first of all, assert that the from address is the correct L1 address that we deployed. So not everybody will be able to send us deposit messages, and add balance, basically. Okay, so this was the other direction. Yeah, I'll repeat. Here we have the send message to L2, and here we have the L1 handler, basically. So, yeah, any questions about that?
How does it work? How do I send messages from L1 to L2?
There is also a mapping. So basically, you add the number.
It calls the StarkNet core contract.
Yeah, it is called the StarkNet core contract indeed, and the operator is by protocol obligated to consume this, and there are safety mechanisms that you might not right now, but will be that you must consume it within X time, or the system will freeze. So.
I send it in the L1, and the operator on L2 consumes it from L1, and there is some security mechanism that ensures that this operator includes this message on L2.
Yeah, and when the proof is in the update state that checks this proof, it also as part of the output of the proof, he sees, I consumed these and these messages, and he knows to reduce them.
The state update won't happen if those messages do not exist. So I can just send a deposit message, a deposit transaction on L2 if a corresponding message was not sent on L1, because then the state update will fail. Okay.
Okay. So okay, I finished the part I want to show you. I think the next thing is for you to try to work on your own on this code. Try and do something nice, something crazy. I know. So this will be. You have time for questions about general things, not necessarily what I talked about Ciro, about StarkNet, about how to do things, and afterwards you can go hack. Yes.
Sort of an architectural design question, but immutable memory is similar to something like SSA and LLVM, right? Like, is there a reason you decided not to just compile that and allow immutable memory and just transform it into some kind of reusable?
Okay. The question was why we decided to go with immutable memory instead of compiling to SSA and using so it will be transparent to the user in a sense. Okay, this works for variables, and there is the rebinding mechanism which basically allows you to do just that, as you saw before. But it won't help you with data structures like arrays and dictionaries and things like this. Yeah. Okay. Any other questions?
The end code to the resources page.
The end code?
Yes, so
Yeah.
you might be able to start.
Yeah. Okay. I'll add this code in a few minutes. Okay. Okay. Go on working. Good luck.
There's like 40 minutes, something like that, and then hopefully if someone will want to present what he did, then we'll be very happy to share it. And try, if you have any questions, we are here now. Also feel free to eat or take drinks.